Yeah, good morning, everyone. Yes, my name is Watanabe from the University of Tokyo. And again, thank you very much for your invitation to IIT Kharagpur. I'm very happy to talk about the aeroelasticity and the aerodynamics in Turbomachinery here in IIT Kharagpur. Okay, so from today, on 3 days course, I'd like to talk about the Flutter, mainly Flutter, it's aeroelastic problems. But in the flow-induced, so-called flow-induced vibration, we categorize the phenomena into Flutter and force response. And this lecture is mainly on the Flutter, but I briefly touch about the force response later. But the first one is the fundamentals of the Flutter and force response in turbo machines. So the general fundamentals were told by Professor Maiti in the day before yesterday. So I don't repeat it, but it's my measure is the unsteady fluid dynamics, aerodynamics. So this talk is from the aerodynamics side, not from the structural side. It's slightly different, but we treat the same problems. Okay? And the second one is analysis methods of Cascade Flutter. So nowadays we have a CFD or numerical techniques. So it's very popular. But these analysis methods are very conventional one with strict analytical methods. So I'm insisting on that because it's on the base of the theoretical work, theoretical understanding of the Flutter programs. So I think it's very important. I'll show you the two methods. One is distributed singularity, and the other is a so-called actuator disk method. So I'd like to talk the very fundamentals of these methods, but it's a little bit troublesome. It's complicated, so it's very hard to understand immediately. But I want you to feel the importance of the analytical methods. And the third one is the experimental techniques. So I'll show you the very general treatment of the experiment for Cascade Flutter, and also measurement technique. So for this measurement technique side, my laboratory has very recent active researches on the usage of the PSP, pressure-sensitive paint. So I'd like to show you the measurement technique and also some recent results in my laboratory. And the fourth one is, yes, from this fourth and fifth are the recent trend and the examples of the recent researches. And these are very practical talks. So from fundamentals to practical talks, only 3 days. So it's an essence. This lecture is the essence of the current Flutter programs and Flutter researches, and conclude my talk. So today I'd like to talk about the first of fundamentals and the first half of the analysis method. And tomorrow I'll talk about the latter half of the analysis method and experimental techniques. And the third day, on Friday, I'll talk about the recent trend and research examples. Okay? But first of all, I'd like to introduce what we are doing or who I am. And this is a campus map of the University of Tokyo. It's the downtown Tokyo is shown here. And my university has 3 campuses. One is the central part, is main campus, is Hongo campus. Yeah, I'm working here. This is the center of the downtown Tokyo. And the second one is the Komaba campus. It's also in downtown, but southwest from the main campus. It's near Shibuya station. And this campus is for sophomore or fundamental studies for the first year and second year students, undergraduate students. In Japanese style, we have 4 years undergraduate course, and 2 years master course, and 3 years, at least 3 years PhD course. That is our system. And we, Hongo campus received third-year students and above. And this campus is the main campus, but we have a new campus in Kashiwa campus. It's northeast from Tokyo. Takes about 45 minutes by rapid train from here to here. But this is a new campus for frontier science and technology. It's a research campus. They have only the graduate course, not undergraduate. So we have 3 campuses here. But in our Department of Aeronautics and Astronautics, we have collaborative professors from JAXA ISAS. JAXA is a Japan Aerospace Exploration Agency. It's a counterpart of NASA in the United States. And they have several branches, but ISAS is an Institute of Space and Astronautical Science. It's a very famous institute. Do you know the Japanese space program Hayabusa and Hayabusa 2? They are managing, this institute is executing this project. So we have 8 professors from here to here. They are helping our education and research also. So whole 4 campuses we have in our department side. And organization of the department. This is a photo in the fall, in autumn. So our campus is famous for gingo trees and gingo leaves in autumn. And in our department, Department of Aeronautics and Astronautics, we have undergraduate course, junior, senior, so 3rd and 4th year in undergraduate course. And we have 55 students per year. And they are selected at the middle of sophomore. So fortunately, our department is very popular to the students. So we have very excellent students from Komaba campus. And they are classified into 2 courses, systems course and propulsion course. So of course, I belong to the propulsion course. And in the graduate school, we have 2 years master course. The number of students is 56 per year. So it means all undergraduate students can enter the master course. But in reality, we receive about around 45 students, master students from our undergraduate course. And from the outside, we have 10 students per year. And after that, we have 3 years course for doctor. And we have about 15 students per year. That is changing year by year. But at the average, we have about 15 students. The problem is we need more doctor students. We'd like to have more doctor students, but nowadays the master students do not come to doctor course not so often. So that is our problem. Not only our department, but also the School of Engineering. So is it same here? Yeah, okay. That is a problem. And they are classified into 4 groups. Group A is Fluid Dynamics, and Group B is Structures and Materials, and Group C is Flight Dynamics and Control, and Group D is Propulsion. And of course, Group C is the most popular for students. And academic staffs, we have 11 professors and 6 associate professors. In our style, the full professor manages 1 laboratory, and we have in that laboratory, we have associate professors. So professor and associate professor are co-workers to manage the one laboratory. So it means our department has 11 laboratories, but we need more associate professors nowadays. And then, as I said, we have cooperated professors from other institutions. So the last one, Japan Aerospace Exploration Agency, we have 8 professors. But from the Graduate School of Frontier Science, it's Komaba campus, we have 3 professors. And Research Center for Advanced Science and Technology, this is located in Komaba campus, and we have also 3 professors. So we have academic staffs, many academic staffs. So for me, I have only 2 two or three master students per year. And my associate professor also 2 or 3. So it means we have 5, 6 master course students per year. So first year and second year we have about 10 master students in my laboratory. Okay, and this is the overview of the research topics of our jet propulsion laboratory. I named our laboratory as UT Jet Propulsion Laboratory. UT is University of Tokyo. And I have this is myself, Watanabe, and I have Associate Professor, Professor Himeno, and 3 assistant professors, Sakuma, Tateshi, and Nam. But Sakuma and Tateshi left last month. So currently I have only one Dr. Nang is as an associate assistant professor. And PhD students, it's old data. I have now 3 PhD students and 9 master students and 6 undergraduate students. This is this year's formation of my laboratory. And our research fields, it's an aeroelasticity and compressed aerodynamics. This is an original research area in my laboratory. I'm the 3rd generation in our department after the Second World War. And from the first to this second generation, my professors, old professors, did many works on the compressed aerodynamics and aeroelasticity. But I expanded this field to another one. And third one is aeroacoustics. It's already unsteady aerodynamics, so it's an original field. But I expanded the research field to the rocket side. It's a 2-phase flow phenomena. It's a gas-liquid 2-phase flow phenomena in rocket engine system, and also sloshing in the liquid rocket tank. This field is mainly managed by Professor Himeno, Associate Professor Himeno. And the other one is jet engine system. It's the general several topics we have. First one is flow and heat transfer characteristics of the surface air cooled oil cooler. That is, I'll show you later, but it's an international collaboration with the European Union. And the next one is electrification of air propulsion. That is a very popular issue nowadays. So we use gas turbines for propulsion conventionally, but we are changing it to hybrid one or electrical one. It's like cars. So this is a trend, very strong trend nowadays. And all over the world are looking at this. But it's for the large size aircraft, it's incompressible to transfer to the electrification in the near future. So we did some this kind of evaluation of the system in this field. And the last one is biofluid mechanics and application. It's my hobby. And I'm interested in the oscillatory flow in the lung system of human or birds or insects. That is very interesting. But the basic idea is we'd like to use the very sophisticated system of the biofluids into the artificial systems. That is, this field is called biomimics, something. Yes. Okay, and I'd like to clarify the system of this kind of oscillatory flow in the lung system. Okay, and the conventional one. Today I talk about aeroelasticity. And the aeroelasticity, we are interested in the flow structure coupled analysis. It's a numerical analysis. And the second one is the PSP measurement, pressure sensitive paint measurement of unsteady blade pressure. And the main concern is the shock associated flutter. As Professor Mistry told yesterday, nowadays it's some very big problem is shockwave behavior in the compressor system and the effect of flow separation, stall. So these are the current very important problems or issues in Cascade flutters. And for compressor aerodynamics, we are interested in the 3D unsteady flow behavior in rotor stator configuration and rotating stall and the casing treatment effect. Casing treatment is the countermeasure of the rotating stall to prevent the rotating stall. And the flow characteristics in humid air compressor. It's a project with an industries. We inject the water droplets into the inlet of the compressor. So it's very effective to enhance the output of the generation, electrical generation. So, but very big problem is erosion, of course. So we are doing some experimental work to measure the droplet size or the behavior of the liquid on the blade. So that is a very, very important and interesting issue. It's a kind of two-phase flow. So it's have a cross connection in these two fields. And we are doing some CFD work on the supercritical CO2 flow. That is also very popular topics in the world to use the supercritical CO2 for gas turbine generation. And the last one is aeroacoustics. It's a generation. Yes, it's as you may know. The source of the sound from the jet engine is exhaust jet, and also the fan. So now we are doing some experimental work on the generation mechanism of broadband fan noise. But formerly we did some experiment on the jet noise and jet noise reduction by some kind of active control method. So these are our unsteady aerodynamics side topics. Okay. And test facility. We have several test facilities for these topics. The first one is transonic linear cascade tunnel with blade oscillation system. It's shown here. And the Mach 1.2 flow comes from here. And I'll show you the results of this test facility later. And the second one is low-speed 3.5 stage model compressor here. We are doing some work on casing treatment effect on the rotating stall in this system. And the third one is an anechoic chamber for noise research, shown here. And M2, supersonic wind tunnel. It's used for the scramjet inlet flow field. It's mainly the shock control or shock behavior to identify the shock behavior at the inlet of the scramjet engine. And next one is low-speed wind tunnel humid air compressor research. It's the airspeed is about 60 meters per second, and we inject the water droplets into the cascade here. And sloshing experiment facility and atomization experiment facility. These are two-phase flow test facilities. And this is a linear transonic cascade tunnel. Okay, I'll skip it because I'll show you later the details of this. And this is sloshing test facility. And we developed a new CFD method to treat the two-phase flow, especially the interface of liquid and gas. It's very, very correctly captured. And we check that CFD results by this test facility. And this is three-stage test compressor. It's very low speed, but rotational speed is 3,800 RPM. That is a design point. And yes, it's driven by the electrical motor. It's 100 kilowatt. It's very small or low speed one. Okay. And M2, supersonic wind tunnel. So now it's used for the fundamental research on the shock control and anechoic chamber for noise research. This is some MAT it's, on the walls, yeah, to prevent the reflection of the sound. Okay, and next one is my one of my research fields. I have an advanced air propulsion laboratory. This is a new laboratory supported by the industry. Do you know IHI Corporation? It's a Japanese industry. It's a top manufacturer of the jet engine in Japan. And this laboratory is fully supported by IHI Corporation, and it's started in fiscal year 2012, and 3 years contract, 3.4 years contract, and it's continued to phase 2 from 2016 to 18. It's finished the last month, March. In Japanese system, fiscal year starts from April to March. So fiscal year 2018 finished at the end of March this year. And fortunately, they continued phase 3 to phase 3. So from this April, so it's a 3 years contract. And I'm taking charge of this laboratory as a concurrent professor. And to phase 2, we had an assistant professor, Tateshi, but he retired, or he moved to IHI Corporation. So I hired new assistant associate professor, Professor Ito. It's not TVD. So from April, I have associate professor Ito. So we are doing 3 research topics. We have 3 research topics. The first one is environmental technology. It's Turbomachinery, Aerodynamics, and Aeroelasticity, noise, etc. And the second one is energy management. Some more electric engine, the electrification of the propulsion. And third one is advanced material manufacturing. So we have a friend, I have a colleague, Professor Aoki. He's specialized in the structures and materials. And they are doing some work on the CFRP application. And also we have collaboration with JAXA. JAXA people who are involved in this activity, this laboratory's activity. And I'm very happy to have this kind of support. And we have, every topics have research meetings every 2 months. So we have very frequently exchange our research information with IHI people. So we can get some detailed information. It's proprietary information from IHI people. And we can, for instance, we are doing CFD work, and they have test data, and we can compare them each other. That is a very good thing for us, collaboration with industry. Okay, and another activity is it's called SHAFE and SHAFE 2 research programs. It's an European Commission special coordinated called EU Japan Aeronautics. So this is one of the projects. European Commission has a contract with the Japanese government. METI is Ministry of Economy, Trade and Industries. And they have a contract. And under these governing, we have the research team. And whole projects are managed, controlled by Rolls-Royce in the UK. And in the European side, they have a collaboration with Brandenburg University of Technology. And in Japanese side, the Sumitomo Precision Products, they are the manufacturer of the heat exchanger. And we are subcontractor of the under Sumitomo Precision. So this side, European side, is funded by European Commission. But Japanese side, we are supported by METI, Japanese government. But we have, it's governed by Rolls-Royce. So it's a little bit, that's okay. And sometimes we have frustration, but it's governed by Rolls-Royce. Okay. And we are doing numerical study on the cooling characteristics of surface air-cooled oil cooler, focused on flow field around cooling fin. It's an yes, the details will be skipped. It's a time limitation. So, but our laboratory executes research as the contract of Sumitomo Precision products aiming at the improvement of the surface oil cooler performance for advanced heat management in jet engines. We established a new code of the conjugate heat transfer analysis based on the CFD. And the Japanese program is funded by Maiti, and our laboratory performs CFD analysis. And results will be used to optimize the surface cooler configuration. So Sumitomo Precision makes heat exchanger based on our research results, and they send it to Rolls-Royce, and Rolls-Royce tests that performance. That is a collaboration, the framework of the collaboration. It's under Horizon 2020. It's a European Commission's project. Okay, so now let's move on to the aeroelasticity. The first one is flutter and force response in turbomachines fundamentals. Okay. Yes, so we call flow-induced vibration. It's the problem of aeroelasticity. And it's a vibration phenomenon due to the interaction between structural vibration and unsteady aerodynamic force. This kind of phenomena are called flow-induced vibration. Very simple example is when a circular cylinder is placed in the airflow, the carbon vortex street is generated. But this carbon vortex street has an effect, so force the oscillation of the circular cylinder, and the oscillating cylinder governs the vortex shading also. So they have a cross interaction with each other. So and the vibration displacement is x, and the aerodynamic force Ft. So they the relationship between these two parameters are very important or critical. So the equation of motion is written like this. So Ft is the right-hand side. It's the source term. This is an aerodynamic force. It's as an external force, it's forcing this oscillation system. And sometimes it's a forced vibration, and sometimes the self-excited vibration occur. So these are the flow-induced vibration, the typical flow-induced vibration. And a simple example is the aerodynamic force is proportional to velocity. So this equation shows the aerodynamic force. It's proportional to the oscillation velocity x dot. And CF is a coefficient, and a positive coefficient. So we, if we put it into here, we can have this form of the oscillation equation. And C asterisk is CF minus C. So this is a damping term. Damping coefficient is minus C asterisk. And the solution is, as you know, this, written like this. And theta is C asterisk over 2m omega n. Omega n is the natural frequency of the vibration system. So here we have theta. So if C asterisk is positive, so this oscillation is unstable. So the oscillation amplitude, displacement will grow with the time. So the displacement increases with time if C asterisk is positive. So this this phenomenon, this situation is a self-excited vibration and called flutter. So the critical point is this damping coefficient. So that is the main issue. Okay, and this is a chart of displacement against time. So this situation is a positively damped oscillation, is stable. But this is a negatively damped oscillation. It's a self-excited vibration. It's unstable and called flutter. And also, but in most cases, the self-excited case, but it's go into the limit cycle oscillation because there is a damping force, like mechanical damping or something, structural damping. Okay, but this situation is also flatter. So yeah, even it goes to the limit cycle oscillation, it's called flatter. So in this situation, the equilibrium is attained between excitation and damping. And it's an energy consideration. So displacement x is sinusoidal, this one. And the corresponding aerodynamic force is shown, it's written like this. So the same frequency, but there is a phase difference, phi. So phi is a phase difference between displacement and aerodynamic force. So this EF is a work done by FT in one period. So this energy or work can be calculated by this integration. So FT is here, substituted this one, and X dot is here, and one period integration. So we can calculate EF as this one, pi F0 X0 sine phi. And ED is the work done by viscous damping force. So C is a damping coefficient, and X dot is a velocity. So we can calculate ED in this by this integration. So the result is pi C omega X0 squared. So the big difference is this is X0 proportional to X0, but it's proportional to the square of X0. So if we draw the graph of E against X0, we can have these curves. This is EF, it's proportional to X0, but this is ED, it's proportional to the X0 square. So we have this situation. But in this situation A, EF is bigger than ED. It means damping, flow work is larger than the damping work. So it's an unstable situation, vibration. Yeah, and at C, but C, ED is bigger than EF. So this is stable case. And here B is the neutrally stable case. Okay. So this is an energy consideration. So we can consider the instability by unsteady aerodynamic force, one side. But the other side, we can consider that by energy consideration. That's the important point. And this is a very simple case of the stall flutter of an airfoil. What is a stall flutter? So this was explained by Professor Maiti on Monday already. But I repeat it very briefly. It's a more simple case than Professor Maiti's explanation. It's a 1 degree of freedom oscillation model. It's execute only 1 degree of freedom. It means only the heaving or translational oscillation in this direction. And the lift force is written like this, rho B U squared, and CL is lift coefficient, and alpha is an instantaneous angle of attack. And instantaneous angle of attack is expressed like this. Alpha 0 is the initial angle of attack. It's at the equilibrium position. Okay? And we have this additional change in angle of attack by oscillation. Dxdt is an velocity of this translational motion. And so we can use this one, this alpha into this CL. And this is an equation of motion. Okay. And lift force is substituted by this one. And alpha is here. Okay. And we expand CL by Taylor expansion like this, and only the first term is used, and over second order term is neglected. So we can have this equation. And x0 is the initial position of the airfoil, and x is then a change from the initial position. So x is written like this, and x0 is equilibrium position. So this equation holds. Okay, so we put this kind of these equations into this equation. We can have the equation for the small x like this. Okay, and finally we can have this equation of the oscillation of the displacement x. And this is an oscillation equation with damping term, and this is a damping coefficient. And this one, CL prime, it's the slope of the lift curve, okay, gradient of the lift coefficient. So if this lift coefficient, the gradient of lift coefficient is negative, the flutter occurs. Okay, so as you know, this is lift coefficient versus alpha angle of attack. Now, this is a normal case, unstall case, but this is a stall point, and over stall point, so this curve is the gradient is negative. So this is an unstable region of this oscillation system. So flutter occurs in this field. So this flutter is directly connected to the stall. So this kind of flutter is called stall flutter. It's a very simple case. But in reality, the oscillation system is 2 degrees of freedom. Yes, okay. So we have also the torsional displacement. So it's a very simplest case. The translational vibration is shown here. And torsional vibration is expressed as this. Okay. So there is a phase difference, phi, between translational vibration and torsional vibration. So in this case, the lift force is expressed as this. So in the former case, we have only this term. But now we have alpha here. It's a torsional vibration. So in this case, compared with the single degrees of freedom, it's a little bit complicated to find the solution of the differential equation. So we calculate the aerodynamic work. So EL is calculated by this integral. So lift force multiplied by the H's, and it's a vibration, yes, displacement. And if we calculate this one, so we use this one here, L, and H here, and the results is shown here. So if EL is positive, this oscillation is unstable. So instability occurs at EL is positive condition. So if we look this one, so we have here dCl d alpha. It's a slope of the lift curve. It's a similar, the same as in the previous case. And we have minus here. And so if this term is positive and this term is negative, EL is positive. So it means a stall flutter. But even this dCl d alpha is positive, we can have a negative damping when this term is negative. Okay, so this is the this condition corresponds to that case. Okay, so this term, the first term is smaller than the second term. If this condition occurs, we have flutter situation. So it means flutter is possible even in non-stall situation in a 2 degrees of freedom case. And phase here, so the phase difference between 2 degrees of freedom is an important parameter. So in the flutter case, always the phase difference, phase is a very important parameter. So please remember it. Okay. And the flutter of a single airfoil or a single blade, the first airfoil blade flutter is airfoil vibration due to some flow perturbation. So airflow vibration occurs due to some flow perturbation. And the change in the aerodynamic force induced by flow change due to airfoil vibration. And the unsteady aerodynamic force has a phase which enhances the airfoil vibration. This is in the case of negative damping. And we have vibration instability. So it's an self-excited vibration, so-called self-excited vibration. So negative damping case. Okay. And in the single airfoil and single degree of freedom, the stall flutter is possible, and non-stall flutter doesn't occur. And the single airfoil, 2 degrees of freedom, non-stall flutter can occur due to the coupling of the translational mode and the torsional mode. So that is the difference, the degrees of freedom. And the cascade flutter, we have to treat the cascade flutter, not single blade. So, but we assume that the same basic mechanisms holds as for the single airfoil. And, but we have to consider the interaction between the cascaded blades. Okay? And oscillation of the all blades must be taken into consideration. And this is a model, analytical model of the linear cascade, oscillating linear cascade. So as I'll show the detail of this later. But this is a flat plate blade here, and the next one and next one. So M is the blade number. The central one is M0, and M equal 1, 2, and -1, -2. And this, yes, in this model, each blade is replaced by the distributed vorticities, okay? So this is expressed as this. So it's an harmonical function of the time. And the next one, the next blade has the same configuration of the gamma vorticity, but it has a phase difference from this one. So interblade phase angle is beta. It's called interblade phase angle. And so the second blade has a 2 beta phase difference. This is minus beta and minus 2 beta. So in this model, in this case, there are same unsteady aerodynamic force on each blade, but there is a constant interblade phase angle, IBPA beta. So it means we have a wavy propagation in this direction of the unsteadiness. Okay, so that is a traveling wave mode expression of the cascade flutter. Okay, but this is a very basic modeling of the cascade flutter phenomena. And this is a map, compressor map. And this is shown by Professor Mistry yesterday. And this is surge line here. And this is a constant velocity line here and operating line here. So we have several regions of the dangerous flutter regions. And the first one is here. It's a subsonic or transonic stall flutter. This is so near the stall line, surge line. It's related to the stall phenomenon. The first one is a stall flutter region, and the second one is choke flutter region. This is also a flutter region in the choke line, near choke line region, and this type of flutter is related to the shock, also shock wave. And third, fourth, and fifth, these regions are high-speed case. And low incidence supersonic flutter and high incidence supersonic flutter and supersonic bending stall flutter. But nowadays, the very big problem is here 1 and 5 and 4. These are the near stall flutter and also the shock associated flutter. These are a very big issue currently. In a former time, there is a potential flutter, so-called potential flutter. It can occur all the operating range here, but it's almost understood. So now it's no problem, but we have a very big problem near the stall line. So that is the current situation. And yes, this is the same chart as the previous one. And we sometimes have this kind of flutter, but this is a surge line, but sometimes we have this kind of limitation of the operating range by flutter problem. So this kind of flutter boundary is called flutter bight. Flutter region cuts into the working range from the surge line. So that's a very big problem. So if there is a flutter bight here, we have to change the operating line to the low efficiency side because we have to have some margin from the boundary. So that is a very big issue. So we would like to understand the phenomenon around this, and we push back this limitation to the surge line, okay? And it is still difficult to predict the flutter limit due to the complexity of the flow field near the surge line. So that is a stall flutter, stall-like flutter. That is a very big problem. This is a traveling wave mode oscillation. It's a bending mode, and IBPA and beta is 33 degrees. It's a torsional flutter. The IBPA is 82 degrees. So we have this kind of flutter phenomenon in the traveling wave mode. And yes, instead of IBPA, interblade phase angle, we often use the nodal diameter, the terminology nodal diameter. It's shown here. It's one nodal diameter is here, and red part and blue part has a phase difference, 180 degrees phase difference. So this is node here. It's called nodal diameter. And nodal circle is circle. It's also the boundary of the phase. Okay. So we can have 3 nodal diameters, but 0 nodal circle. But 2 nodal diameters with 0 nodal circle, or 3 nodal diameters and 1 nodal cycle. So IBPA has N is nodal diameter. So IBPA has a relationship with nodal diameter shown here. Okay, and it's a forward and backward. Forward oscillation, vibration. Forward traveling is in this direction, and backward is clockwise direction. We have both cases, and the relationship between nodal diameter and IBPA is here. So because IBPA is only, we are focusing on the blade only, but nowadays, sometimes, so disk itself is a vibration system. It's included in vibration system. So nodal diameter is more practical nowadays for the realistic vibration. Okay. And this is the example of the LPT flutter. So it's this experiment was executed in JAXA, and flutter experiment was executed in JAXA LPT rig. It's a cooperative study with the IHI and JAXA, and they made a low pressure turbine rig, and they put it into the wind tunnel. And they made two kinds of low pressure turbine. One is flat, so based on their design, so LPT, flutter cannon car. And the other one is flutter free Cascade. And they tested them into the same wind tunnel. And they got success. So because this is designed, flutter design, the LPT. And they have, so really here they got a flutter case. So realistic cascade flutter was observed in the testing. That is a very rare case all over the world because this kind of experiment is very dangerous. So if we detect the flutter, we have to stop the wind immediately. So my student watched that. So he pushed the stop button. So he was very responsible for this one. Okay. And the vibration displacement rapidly increased from 67% of the reduced flow rate, and the limit cycle was established finally. And the IBPA was not uniform, so because of the blade mistuning. So in the realistic case, so the blade itself is not so uniform. So blade mistuning means the difference between the structural characteristics of the blades, between the blades. So for instance, the frequency, natural frequency is not identical for all blades. So that is called mistuning. So in this, so due to this mistuning, there is not a constant IBPA in the realistic case. But in the ideal model, we use constant IBPA usually. Okay. Okay. So next one is, so it's not flutter, but I touch very briefly on the forced vibration of the cascade. So yesterday, Professor Mistry talked about the unsteady phenomena or unstable phenomena, flow phenomena in the compressor and turbine. And it's a very good summary of the whole phenomena. And from the aeroelastic point of view, there is an exciting force caused by the flow instability or flow unsteady flow. So very typical source of the exciting force is, we have four typical sources. The first one is aerodynamic interaction between structural components. That is potential interaction or wake interaction or vortex interaction. For instance, stator-rotor interaction or strut-rotor interaction, the bleed-port-blade interaction. There is many sources of the exciting force in this category, or measurement probe or structural component, something. Okay, so this is a very representative source of the forced vibration. And the second one is surge, and third one is rotating store and in the distortion. These are, for instance, surge is one-dimensional flow oscillation in the axial direction. So this is a cause of the exciting force, of course. And rotating store is the two-dimensional and the circular movement of the store region. This has also the exciting force. And inlet distortion, if there is an inlet distortion, so rotor blade can experience the flow variation per one cycle. So that is also the source of the exciting force. And the representative one is rotor-stator interaction. So this is an inlet guide band and rotor blade here. So the wake of the inlet guide band is cut by the rotating cascade like this. And in this situation, this is a measurement of the aerodynamic force on the blade. It's executed in MIT very long time ago. It's a rotor blade here. And this is stator. And there is a transducer on the stator blade. And they took these data. It's an time, and this is an axial force, and this is tangential force. It's an axial force. So both are same. So there is a periodic change in the aerodynamic force. So this is an exciting force. Okay. And this is the CFD results of the turbine. The trailing edge of the nozzle here, and it's a rotor. And this is entropy contour. As we can easily see the low energy wake region here. So this is a boundary layer on the suction surface of the nozzle. And the wake comes here and flow into the rudder channel like this. So in this situation, so rudder experiences a very big change in the aerodynamic force. And so we usually use the Campbell diagram to evaluate the excitation by this kind of force response. And the excitation frequency is called engine order. And natural frequencies of blade are plotted together here in the Campbell diagram. And this is shaft speed, RPM. And this is frequency. And this green line shows the engine order. Okay? So if we have one eccentricity in one circle, in the circumferential direction, this is engine order 1. For instance, we put a probe into the compressor. This is a source of wake. So in the downstream blade, they experience one time per one cycle the excitation. So that is engine order 1. And engine order 2, or if we have 100 stator blades, we have 100 engine order. Okay? So this is proportional to the shaft speed. Okay? And this blue line shows the natural frequency of the blade. Okay? So it's a first bending usually, and second, first torsion or second bending or something. So it's depend on the structure of blade, each blade. And this is an exciting force, and this is the blade natural frequency. If they correspond each other, it's very dangerous. So it's, and cross points correspond to the candidates of the resonance. So resonance, at the resonance condition, the blade vibration occurs very hard. And the crossing must not be included in normal operating range. So if we have a normal operating range here, so there is no crossing point, so it's okay. But if we have one crossing point like this, we have to consider the design. So there are two methods to avoid resonance. So the first one is changing the blade count or something. And the second one is change the blade structure to change the resonance frequency, natural frequency of the blade, each blade. So we can use two methods, but usually, so the change of blade structure is very difficult. Yes, so usually we use the changing the blade count or something. So number of the structural components. Okay. So engine order is the number of perturbation source in circumferential direction multiplied by rotational speed. So we can predict this kind of cross points at the design. So, ideally, we can avoid this kind of excitation so at the design phase. But very often we experience this kind of vibration in the testing. So sometimes we didn't realize the source of the instability. So that is a problem. So, but we have to do the careful treatment of this camber diagram at the design phase. Okay. And on the other hand, we have damping force in the compressor and turbine. And we have three kinds of damping force. The first one is aerodynamic damping. So usually aerodynamic force on a blade acts as a damping force. But sometimes we have negative damping force, and it's a flatter case. But second one is structural damping. For instance, so blade root. This is so Christmas tree or dovetail structure here. And this is originally this is a little bit loose, so not strictly fixed. And during the rotation, there is a centrifugal force, so this is fixed. But there is some looseness at the root. So this is a damping force, mechanical damping force. It's a very big effect on the damping. And also the shroud here has friction between the adjacent blades. So this is also the source of the damping force. This is the most effective damping force. So if there is some possibility of the vibration, we use the mechanical structural damping very big. So that is a very effective method to damp the vibration. And there is an internal damping of the material. It's a friction damping in the material, but it's very small. So it's not, it's almost negligible. So we use structural damping to prevent the vibration usually. And the countermeasure against the forced vibration is, of course, camber diagram. So it's a detuning. So tuning the blade count or tuning the natural frequency. This is a detuning. And or an increase in the structural damping. So sometimes this is a turbine, root of turbine, and there is a Christmas tree structure. There is damping here. But if we need more, so there is a damper here. So a thin plate is placed here to absorb the vibration energy. These are the typical countermeasure. Okay. So we have a rest. Okay. Thank you very much. Cascade flutter. Okay. Yeah. For analysis methods, we have two representative typical methods. The one is a distributed singularity method, and the other is actuator disk method. So these methods can obtain the profound insight of the physical phenomena of the flutter, and we can clarify the parameter dependency very easily. So these are the powerful and indispensable methods for analytical approach to flutter phenomenon and understand the physics of the flutter phenomenon. But there is a strict restriction of the potential flow assumption. Okay? And another one is, of course, the numerical simulation based on the CFD, computational fluid dynamics. So this kind of numerical simulation is capable to analyze flutter including viscous effect the boundary layer effect or stall phenomenon, etc. And nowadays, there is a big rapid progress in the fluid structure coupling analysis for realistic simulation. So we can use this kind of numerical simulation even in a commercial code. There is a capability of fluid structure coupling. So it's, I think it's easier for you to access. But in this lecture, I'd like to explain the detail of the analytical methods because, as I told you, it can obtain the profound insight of the physical phenomena, the physics of the flutter oscillation. That is more important for this kind of basic lecture. Okay. So from this page, it's a little bit complicated, so please be relaxed. And we can use so-called thin airfoil theory. So it is available for obtaining steady and unsteady aerodynamic force acting on a blade. This is a model of the airfoil, and there is mean camber line here, and blade thickness here. So blade thickness is of course, very important parameter. But in this theory, it's neglected. And it's only an airfoil is composed of only the mean camber line shown here. Okay, that is a thin airfoil theory. And a steady airfoil theory. The first, when a flow starts and a circulation around an airfoil generates, an equivalent counter vortex is shed from the trailing edge of the airfoil based on Helmholtz conservation law of the vorticity. And the shed vortex is transported to far downstream region by the main flow. And the velocity is assumed to be the same as that of the main flow. And the third, after sufficiently long time, the vortex is transported to infinitely downstream position, and an amount of circulation is left on the airfoil. So this is an circulation, but the counter circulation is placed on the far downstream. Okay, so there is no vorticity on the whole field. And fourth, if Kutta condition is imposed on the trailing edge, the circulation around the airfoil is uniquely determined by this theory. So Kutta condition is in this situation, there is no flow around the corner. That is a Kutta condition. And then this thin airfoil theory can be expanded to unsteady airfoil theory. So the circulation is maintained the same amount. But when a circulation around an airfoil changes in time due to airfoil oscillation and or flow perturbation, the free vortex is shed from the airfoil at each moment. Okay, so this is compensate. This compensates the change in this circulation of the airfoil. The shed vortex forms a continuous wake vortex sheet till infinitely downstream location. And the wake vortex sheet includes flow velocity on the airfoil, induces. The wake vortex sheet induces flow velocity on the airfoil surface. So this wake vortex affects the blade force every time. And not only the circulation on the airfoil, but also the circulation induced by the wake vortex sheet must be considered in the estimation of the circulation around the airfoil. So this is an unsteady airfoil, oscillating airfoil theory. And for Cascade, so this is singularity analysis. It's an expansion of this consideration to the Cascade. So this is the same model as the previously shown. So there is a brace, so infinite number of braids. It's a linear cascade, and the braid number is the central braid is number is 0, and 1, 2, and -1, -2. Okay, and these are oscillating, and oscillating braid surface is replaced by vortices shown here, And distributed vortex on the surface is expressed as gamma B. And this is called a bound vortex. And C is a local coordinate on each air for each blade. And the circulation change due to blade vibration is equivalent to the bound vortex change in time. And according to the change in bound vortex, a vortex gamma W is shed from the blade to the wake following the vorticity conservation law. Okay? This is gamma W. It's a wake vortex. The shed vortex is called a free vortex or a wake vortex here. Vortex sheet is formed here. Okay? And so important point is we have to consider all the vortices in the field. So we have bound vortices in each blade, and also wake vortex sheets in the downstream of each blade. So there are many, many vortices in the field, and we have to consider all the influence of these vortices in the field. And we'll calculate the induced velocity on the blade. And in this direction, the y direction. And it's induced by all vortices in the field. And the representative blade is here, number 0. So this is a component of the y direction induced velocity, Vsx0. And this is calculated by this equation. So this is I'll explain the details, more detail in the later, but we can calculate the induced velocity by this equation. It's an Biot-Savart law. Okay, and gamma B is here, and gamma W is here, and the summation is m from minus infinity to plus infinity. So there are infinite number of blades. So this is we need summation, and the integration is bound vorticity is located on each blade. So this is a surface integration on the blade surface. And this is wake vortex. So the integration is from the trailing edge to the minus plus infinity. So it's a downstream field. Okay. So we can calculate the induced velocity here. And in this equation, we have gamma B and gamma W. So bound vorticity and also wake vorticity. But these are not independent because gamma W is shed from gamma B. So the relationship between gamma W and gamma B is shown here, expressed like this. So I'll explain the details later. But we can have a relationship between gamma W and gamma B here. So we put gamma W here in this equation. We can have this equation, integral equation. Okay, and we have gamma B here and gamma B here. So in this equation, we only have gamma B. So gamma W is eliminated from this equation. Okay, and the boundary condition is a non-permeable condition on the blade surface. So there is no flow across the blade surface. So it means y component of the velocity is 0. So this non-permeable condition gives an integral equation for gamma B because this is 0 or the oscillation velocity is inputted here. So we can have the integral equation which determines gamma B. So if we can obtain gamma B, we can calculate aerodynamic force on the blade. So lift force is here. So gamma B is integrated from leading edge to the trailing edge. And this is a non-dimensional coefficient of the blade force. So F is divided by rho cu q. Q is the blade oscillation velocity. And it's an, real part is CR, and CI is imaginary part. And in this formulation, CR, real part is the proportional to the blade oscillation velocity. So in this terminology, so real part is represents the exciting force. So if CR is positive, the oscillation is unstable. That is an overview of the framework of this method. Okay. And again, in this model, there is an interblade phase angle between the two. So it's a constant interblade phase angle beta. Okay. So there is the same unsteady phenomenon, aerodynamic phenomenon on each blade, but they have a constant interblade phase angle between each adjacent blade. Okay, so there is a wavy motion so transported into this direction, cascade direction. Okay. That is the modeling of this cascade flutter. And the other one is actuator disk method or actuator disk theory. This is a realized theory with the small perturbation assumption, and the cascade is replaced by discontinuity service in a duct flow. So this is a linear cascade. But if we look at it from far position, we can see like this. So cascade is very thin plate. So that is called actuator disk. So and the flow variables are described separately in the upstream and downstream regions on the disk. And after that, we connect the flow field by the connecting condition or boundary condition at the disk interface. And this treatment determines the all variables from upstream to downstream. And it's applicable to three-dimensional also. It's an hub and tip. And if we look this situation from the far field, we can see it as a very thin plate. Okay, this is an actuator disk. And this is a control volume in each channel. Okay, so connection condition, boundary condition is through the control volume. The first one is mass conservation, and the second is energy conservation. And third is total pressure loss at the leading edge. And the fourth is conservation of the span-wise momentum at leading edge. And the fifth is Kutta condition at trailing edge. This is a three-dimensional case. But I'll show you the more simple two-dimensional case. But in this case, in the distributed singularity analysis, this is purely mathematical and no empirical factor in this method. But in the actuator disk, there is some empirical parameters. So from first one to the fifth one, what is the empirical one? It's a third one, total pressure loss. Total pressure loss cannot be evaluated theoretically. So we use, as an boundary condition, we use usually experimental data. So that is a semi-empirical theory. But on the other hand, this method can be used for stall case or something. Yes, we can use the stall case via total pressure loss data. So this singularity analysis is very strict, correct, mathematical. But it cannot be used for stall case or so. Viscous effect must be eliminated. So, but yeah, this actuator disk method is also a theoretical case with potential flow analysis. But we can use semi-empirical parameter here. So we can expand the region of the applicability to the store case by this method. So both have a good point and bad point. So we can select this. Or for me myself, I use both for analysis. Okay, and after this computation, we can have this kind of results. So the typical one is aerodynamic damping parameter and against IBPA, interblade phase angle. So we can have, if we change the IBPA, we can have the aerodynamic damping results like this curve. Sometimes it's called S-curve. And in this expression, if the aerodynamic damping is negative, it's an unstable situation. And if this is positive, this is a stable condition. And each point corresponds to the several IBPA or nodal diameter. So, for instance, this case is unstable case, and this is nodal diameter 6, the least stable mode here. And sigma is an IBPA, interblade phase angle is minus 90 degrees, nodal diameter 6. And here it's a stable case. This is an IBPA of 15 degrees and nodal diameter 1. Or in such expression, we can evaluate the stability of each cascade or each flow condition case. And also, this is the results of my research in the former research. Also, we can have this kind of expression. The ordinate is E. E is unsteady aerodynamic work, yes, as I showed previously. So it's an unsteady aerodynamic force multiplied by vibration velocity. So that is the exciting energy. So if exciting energy, unsteady aerodynamic work is positive, this is unstable. And if it's negative, it's stable. So we can have this case, also this expression, we can have this kind of S-curve. And if these are, the positive cases are unstable, flatter case. And then we can also use numerical analysis of flow-induced vibration, as I said previously. And we can treat the complicated unsteady flow phenomena and the displacement of solid boundary, the consideration of the structural characteristics, they are possible in this numerical analysis. But the it's from the CFD side, the flatter is very difficult target, and but it's widely used for obtaining the information of occurring phenomena and background mechanism of ray vibration in a qualitative manner. But it's difficult to obtain the quantitative prediction of the physical properties, such as unsteady aerodynamic force. And the very big problem is computational load. It is likely to grow huge when complicated and realistic aerodynamic factors are taken into account. So even using the supercomputer, sometimes the computation takes several weeks, or in our case, it's 1 month or 1.5 months to obtain the converged results. So that is a very difficult issue. And but we have the situation is quantitative prediction versus load reduction. So load reduction is a very important point, and many people are struggling to reduce the computational load nowadays. And nowadays, flow structure coupled method is becoming very popular. So we can utilize this kind of technique. This is the example, validation of the flutter simulation in my laboratory. So yeah, this graph shows the unsteady aerodynamic force and a comparison with the experimental results. And this is a pressure amplitude and phase angle. And this is amplitude. And also phase angle is shown here. And yeah, symbols are experimental results, and lines are computational results. So we could have very good agreement. And this is a reduced aerodynamic work. So it's an E in the previous chart. So if this work is positive, the vibration is unstable. So it's an experimental results, and the red line is computational results. So we have satisfactory agreement by this method. Okay. And we used, as an experimental results, we used standard configuration. So this is we have this kind of standard configurations from standard configuration 1 to standard configuration 11 now. So this is provided by KTH in Sweden, Royal Institute of Technology in Stockholm. So we can get this information from the website of the KTH. And we use this configuration very often to validate our computation. Okay, so at this moment, I'd like to move on to the last part of this textbook. Please see page 90. And I have another material. It's on a PDF. Okay. So I'd like to show the details of the oscillating airfoil theory and the oscillating cascade theory. Okay. It's an singularity method. Okay. It's a little bit troublesome. And the first part is steady thin airfoil theory. It's the most simple case. A simple example of distributed singularity method and steady thin airfoil theory, as I explained the outline in the previous slide. And so we neglect the thickness and use only the mean camber line because the lift coefficient is mainly governed by the camber. So we use thin wing and thin airfoil. And the airfoil is replaced by a mean camber line. And the vortices are distributed on the mean camber line shown here. Okay. So the airfoil is expressed as the vortex sheet, and the aerodynamic characteristics of the airfoil are determined by the vortices. And the vortex strength per unit length is gamma. S is a local coordinate on the airfoil. And circulation around an airfoil is calculated by this integral, the gamma from leading edge to trailing edge. It's a capital gamma is circulation. And the analysis procedure is shown here from 1 to 6. So we put the unknown vorticity gamma is distributed on an airfoil, and the induced velocity by gamma is obtained by Biot-Savart law. And the velocity boundary condition, so it's a non-permeable condition. And the airfoil provides an integral equation of gamma. And the distribution of gamma is obtained by solving the integral equation and calculated capital gamma and calculated lift and moment. That is the analysis procedure. It's a very simple one. And boundary condition is shown here. So non-permeable condition. There is no flow through the airfoil surface. So the normal component of the velocity must be 0 on each location of the airfoil. So Q is induced velocity at x equals x here, Q. Is induced by the distributed vortices on the airfoil. Vortice text is gamma at the coordinate x. So it's distributed from here to here. And Q is the velocity, induced velocity at point x0. Okay? And the U infinity is the velocity vector of uniform flow. The Vn is here. It's a normal component of U infinity. And Vn is shown the next page here, this one. And Vn is the component of, Vn is component of U, it's okay. So boundary condition on the airfoil is Vn plus Qn equals 0, okay? It's non-permeable. And we use this kind of, model. And a two-dimensional airfoil. We consider only the two-dimensional airfoil model as shown in this figure. And the vortex strength on the position x is gamma x ds. And the induced velocity is shown here. Din is here. Dvin is here. This is an induced velocity. Vn is the component of U infinity. But dv in is induced velocity component here. And so it's induced by gamma, the vorticity. So it's expressed as this. It's a Biot-Savart law. And the normal component of dvn is dv in comma n. Okay. So this is shown here. It's delta 3 is this angle. Okay. So dv in n is here. Okay. And so r and ds. R is distance from vortex point and the evaluation point of the velocity. Okay. So it's expressed as this one. And ds is the local coordinate. It's here, shown here. So this r and ds is substituted into the these expressions. The v in n and vn is calculated like this. So v in n is expressed like this. It's the Biot-Savart law. So gamma is integrated from leading edge to trailing edge. This is vortex distribution on the blade. Okay, and Kutta condition is expressed as gamma trailing edge is 0. And Vn is the normal component of U infinity, so it's expressed like this. So the boundary condition is Vn plus V in n equals 0. So this equation corresponds to the integral equation for obtaining gamma x. So this expression is equals to this expression. The unknown is on gamma only. So we can have the integral equation for determining gamma by this boundary condition. So this is a general expression. So the next one is a very simple example. The flat plate airfoil with small angle of attack. So thin wing and delta 1, delta 2, delta 3 is very small. And dy dx, the slope of the airfoil is also very small. And angle of attack is also very small. So the integral equation is expressed as here, very simple one. And we use the coordinate transformation from x to theta. So we have this expression of the integral equation. And at the trailing edge, theta equal pi. And at the leading edge, theta is 0. Okay? So the integral is executed from 0 to pi. And we are using a flat plate airfoil, so dy dx equals 0. So this one is 0. So very simple integral equation can be obtained, as shown here. And the Kutta condition is here, gamma pi equals 0. So from this equation, this is an integral, we can find the solution in the textbook of integral equation here. So in this case, we can have the expression, expression of gamma theta like this. Okay, and the leading edge theta equals 0. So theta equals 0 means gamma theta is going to the infinity. It's a singularity point because this is a leading edge of the flat plate. So this is a singularity point. Okay. So this is CP versus core, and there is a singularity here. And the lift force is given by this expression. Rho U infinity gamma is integrated from leading edge to trailing edge. So if we calculate this one, we can have lift force as rho U infinity squared alpha C pi. Okay? And this is a strict solution of the flat plate lift. So CL is so expressed 2 pi alpha, and the gradient of lift force coefficient is 2 pi. Okay, CL and alpha, and the slope is 2 pi. This is very famous results of the CL alpha curve of the thin airfoil or flat plate airfoil. Okay. And this is a very simple framework of the singularity method. Okay. Okay. Yes. So we can expand this theory to the oscillating airfoil. Okay. So that is more complicated, but I'd like to talk about this this part very. The beginning of this part will be presented in the morning session, and mainly I'll explain it in the afternoon session. Okay, so oscillating airfoil theory. So it's the first one is small perturbation theory in incompressible potential flow. So this is a thin airfoil model in a three-dimensional field. The we consider thin airfoil shown in figure 2.1 placed in a steady uniform flow with velocity u. The airflow exists near the origin of XYZ coordinate system. And the thin airfoil is placed on the almost the same plane as XY surface. The airfoil is oscillating with small amplitude. That is a description of this theory model. And there is a velocity potential. It's phi, capital phi. And this potential is the Laplace equation 2.1. Okay? And if the small perturbation velocity in the XYZ directions are denoted as u prime and v and w respectively, the velocity in each direction is expressed as this one. So we have, in the x direction, we have uniform flow, capital U. So the perturbation velocity in the x direction is capital U plus u prime. And y direction and z direction, we have only the perturbation v and w. And by introducing the perturbation velocity potential phi, the field potential is written as this one. So it's capital phi is the velocity potential for the field, but the small phi is the perturbation velocity potential. So it's only the perturbation. Okay, so we can have this relationship between the ground potential, velocity potential, capital phi and small phi. Okay. And the perturbation velocity in the each direction is related with phi by this. So d phi dx is u prime, d phi dy is p, and d phi dz in w. Okay, and we substitute 2.4 into 2.1 within the Laplace equation of phi. So capital phi satisfies the Laplace equation, but small phi perturbation potential also satisfies the Laplace equation like this. So, and in this, by using perturbation velocity potential, we can write the equation of motion like this: u prime plus d phi dt plus p minus p infinity divided by rho infinity equals 0. Okay. So rho infinity and p infinity is a reference pressure and reference or uniform flow pressure and uniform flow density. Okay. So this is a perturbation equation of motion. And the boundary condition is written like this. So non-permeability on both upper and lower surfaces on the airfoil. It's divided on the upper surface and lower surface. For upper surface, as this is the W is the velocity in the z direction here. It's 3 dimensional, so in this direction is so d phi dz. The limit of d phi dz across z going to 0 plus. So this is u is upper surface. So dzu dt plus u dzu dx. This is the velocity of that's the airfoil, and this is a lower surface of the velocity. Okay, so. So this is an general framework. So we can solve this 2.5 equation by this boundary condition. So if we can do that, we can obtain the flow field perturbation parameters by this theory, the framework of this theory. And this is only the velocity field equation. So we need 2.6 to obtain pressure or force. So this is combined together to get the necessary parameters in the perturbation flow field. Okay. And it's a general expression. So we proceed to the two-dimensional oscillating airfoil theory in incompressible flow. So the governing equation in two-dimensional flow field is 2.8. So we have only x and y. Okay, and the boundary condition is here. And yes, we have thin airfoil. So we don't use the U and ZL, but ZA is enough for us. So the boundary condition is WA is equal to this one. So that is non-permeable condition. Okay. So we solve 2.8 on the boundary condition 2.9 and Kutta condition. This calculation gives the aerodynamic characteristics of the two-dimensional oscillating airfoil. And so in the case of oscillating airfoil, the unsteady vortices are shed from the trailing edge. Thus the vortex exists not only on the airfoil surface but also on the wake surface. So we use this model. So as shown in the previous slide on the Cascade case, this is a single airfoil So this is an airfoil expressed by distributed vortices gamma A. And gamma W is shed from gamma A to the infinitely downstream. Okay, and this is so we will calculate the induced velocity on the airfoil, and we place the boundary condition, a non-permeable condition on the induced velocity, and then we can have the integral equation which determine the gamma A. That is a framework, the general framework. So I'd like to stop this point in the morning session and continue in the afternoon session. Thank you very much. Thank you.